Okay, so the exam will be tomorrow, your first midterm. Everything is included, including the things that we will be discussing today. So I suggest you to ask many questions so that we don't cover new subjects. And well, after our midterm, there is another exam, so we will not be able to extend the time of the midterm. So I strongly suggest you to come on time and take your seat so we can start on time and end on time. You are probably aware of the additional security features on campus. Just to avoid any problems, make sure that you try to come early. I mean, especially if you are living out of campus, there is quite likely that there will be huge queues in the entrance because there are also other exams and many people will be entering in the morning. Well, the other exam starts at 10, our exam starts at 9:30, so hopefully you will be on campus before the other students are on campus. Yes, we will be just downstairs. Hopefully the door will be open. And well, we have already sent permission requests for your entry if you are not living on campus, so you shouldn't be having any problems entering, but just to make sure that you come a bit early. Yes, now your questions. Which other method? The multiple expansion. So what would you like to know? What example? Okay. Did you check the questions on the book? Tell me a question and I will solve it. Come on, at least you should do some work. So what kind of a charge distribution would you like to imagine? Let us look at this charge distribution. Well, we can even put some CL, some coefficients, take some superposition. Well, we said that Legendre polynomials form a complete set. Any function of theta you can write in terms of the Legendre polynomials, PL of cosine theta. The charge distribution, whatever the charge distribution is, it is a function of theta. So you can write it, it's theta dependence at least, you can write it in terms of the Legendre polynomials. I'm just assuming that we have this chart uniform, the radial distribution is uniform. It only has the step function behavior. So you have this sphere. Inside this sphere, you have some charge, some uniform, radially uniform charge distribution. But of course, the angular dependence will have some dependence. Let's calculate the moments, multiples. Now we know that we had seen that this potential of this charge distribution can be written in terms of, let's say, QL over r to the power L plus 1, L from 0 to infinity, where QL was equal to the volume integral of this charge density, r to the L and PL of cosine theta. So if we can calculate QL for this given charge distribution, we know the potential. Well, let's just put the definition of the charge distribution over here. QL will be equal to d cubed r. Well, let me just change the summation variable because this L over here is not a summation variable, whereas the L in the definition of the charge density is a summation variable. So those two L's are in fact different indices. So let's just make this explicit by calling the summation index L prime. Now we can separate the radial integration and the angular integration. And the radial integration will be just, let's take this summation over L prime out. The radial integration is just r squared dr. I have this step function which tells me that this integrand is 0 if small r is larger than this capital R. So the upper limit of integration, I can just replace it with capital R. Within this interval, the step function is just 1. Now in this definition, I also have r to the power L. So r to the power L, this is the radial part of my integration. Then I have CL prime. The angular part will have 1 phi integration over phi. Well, phi changes from 0 to 2 pi. And then another integration over cosine theta. Well, you can write it in terms of cosine theta or in terms of sine theta d theta. So cosine theta changes from -1 to 1. Or let's write it in terms of sine. The theta, sine theta. Theta changes from 0 to pi. PL of cosine theta. PL prime of cosine theta. Which is equal to L prime, CL prime. Well, the R integration, we can trivially evaluate it, capital R to the power L plus 3 divided by L plus 3. Nothing depends on phi, so phi integration just gives us 2 pi. And we know the properties of the Legendre polynomials. If you just have this combination, the integral is 0 if L and L prime are different, and it is 2 over 2L plus 1 if L and L prime are the same. And QL is equal to, well, this Kronecker delta just tells me that in the summation over L prime, only a single term contributes to the sum. And only the term where L prime is equal to L contributes. So the final answer is CL r to the power L plus 3 divided by L plus 3, 4 pi over 2L plus 1. So if we can determine these multiple moments, we are actually able to determine what this CL coefficients in our expansion is. So we have an explicit expression of QL, just put it in the expression for the potential in terms of the multiple moments. So V of the potential at the point R created by this charge distribution will be sum over CL r to the power L plus 3, 4 pi over 2L plus 1 times 1 over r to the power L plus 1. Well, let's see, what did I forget here? Okay, that is one thing I forgot. By the way, this is the potential at this point along the z-axis. So it's not the potential at an arbitrary point, but it's the potential along the z-axis. Yes, question? Well, because I used it in this form. Well, usually you put it over here, if you prefer. The final answer will be the same.
Peki hocam, hiçbir eksen üstünde olmasaydı bu yük?
Well, there are ways of evaluating the potential over here in terms of multipoles. I'm not so sure you would be happy to learn it yet. You will learn it, don't worry, eventually. Now let us look at the shape of this potential. So let's assume that C0 is non-zero, CL is equal to 0 if L is non-zero. What does the charge distribution look like? So basically, since we can write the potential in terms of these multiple moments, or in terms of these CL constants, so by measuring the potential, how it changes as a function of the distance, we can basically determine what the CL coefficients are. And so let's see what these CL coefficients tells us about the charge distribution. Well, if only L equal to 0 term is non-zero, then rho of R is equal to C0. Let's look at the definition. We have this step function C0, P0. And P0 of cosine theta is just 1. Well, it's a uniform charge distribution in the sphere. A uniformly charged sphere is spherically symmetric. C1 is non-zero. All other CL is equal to 0. Let's look at this shape. Then rho of R will be C1, theta of R minus R, P0 of cosine theta, P1 of cosine theta, which is C1 theta R minus R of cosine theta. So again, it is, if you show the x and the z axis only, again, it's spherical. It's a sphere. And the charge density is non-zero only within this sphere. If theta is less than pi over 2, it is positive. If theta is larger than pi over 2, it is negative. So here it is positive, assuming C1 is positive. So close to the xy plane, it becomes neutral, and then in the negative half plane it is negative, lower half plane. Now you have the positive charges on one side, the negative charges on the other side. So that is what we had actually defined as a dipole. We have the separation of the positive and negative charges. So if C1 term is non-zero, that is, if the charge distribution has a dipole moment, it tells us that the positive charges are accumulated on one side and the negative charges are accumulated on the other side. Now let's look at the other terms. L is equal to 2. CL is equal to 0 if C2 is non-zero. CL is equal to 0 if L is not equal to 2. Then rho of R is C2, the step function. P2 is 1 over 2, 3 cosine squared theta minus 1. So you see this function changes sign when cosine squared theta is equal to 1/3 or cosine theta is equal to plus or minus 1 over square root of 3. These are the points at which it changes sign. So what are these angles? Which angle has the cosine 1 over square root of 3? 30 degrees. So this is, let's say, 30 or 60? None of them. Well, cosine of 60 degrees is square root of 1 over 2. Cosine of 30 is cosine of 60 is square root of 3 over 2, not 1 over square root of 3. Well, some angle. Let's say somewhere over here. And also somewhere over here. So you have positive charges here. That is when cosine theta is equal to 1 and close to cosine theta is equal to 1 and cosine theta is equal to minus 1. You have positive charges. When cosine theta is equal close to 0, you have negative charges. So you see this configuration, this is so-called the quadrupole moment. It's not really the positive charges are shifted more to one side and the negative charges are shifted to the other side, but rather than positive charges are shifted in extended symmetrically in one direction, and the negative charges are extended symmetrically in the opposite, in the other direction. So if there is a quadrupole moment, this is what the shape will look like. Now, of course, in general, any charge distribution will have all of these moments. So you will have a more or less a given charge distribution. But in this charge distribution, some regions might be more positively charged than the other half. Even in this one, the positive charges might be accumulated on not the top part, but the top left part and the bottom right part, for example. This is what tells us that there is a quadrupole moment. So directly measuring these quadrupole moments, we can say something about how the charge distribution looks like. Then you can also talk about higher multiples, and basically you will be dividing your region into more and more parts. Now, in this lecture, we will be mainly using the dipole moments. So they will be also important in the polarization of the medium. Well, just a reminder for you too, for the exam, remember to try to come a bit early, because there might be huge queues in the entrance. There's also the chemistry exam. So there will be lots of students trying to enter the campus. Well, if we have problem entering the classroom downstairs, I am thinking about going to the seminar room. I'm not so sure that it will be warm enough outside. And it won't be comfortable. Yes, other questions? About any of the topics that we had covered, not necessarily what we had covered this week. So is there a specific thing that you didn't understand, you couldn't follow? Okay, let me just give some of the basic steps in why we are defining these multipoles. Now, a realistic situation would be we have some charge distribution, rho of r, and we are making an observation at a faraway point. Typically, this is what we will be facing. In this case, the potential at the point r will be just the integral of this charge distribution over its distance. This is the point r prime within our charge distribution. Or let me put it in a different way. You assume your origin to be within the charge density. That would be, you don't have to, but that is the case that it makes the most sense to make this multipole expansion. So you are making an observation at this point r, whereas your charge distribution is at the point r prime. Now, since if you look at this distribution, r prime is much smaller than r, typically. So you have a small parameter, and whenever in physics you have a small parameter, you can talk about approximate answers. Well, the experiments will always be approximate. They will have error bars, so there's no harm in having error bars in our theory. I mean, there's no point in having exact numbers if you cannot compare it with the experiment. So approximate theory and approximate experiment, a good combination. Most of the time, we don't know what rho is, but we can make an I mean, rho is just a function. In a sense, it has infinitely many parameters. A function has infinitely many parameters, but we can express this potential in terms of just one or two unknown parameters which we can measure. So that will be a good enough description of this charge distribution. So we have this small number, and in terms of this small number, we had discussed that this 1 over r minus r prime, it will be, well, at very far away distances when r is very large, it will just look like 1 over r. Of course, we have some corrections. The corrections will be proportional to powers of this r prime over r to the power L. It's just like a Taylor expansion. And of course, this Taylor expansion will have certain coefficients. This parameter over here depends on the magnitudes of these vectors and also on the angle between the two. So the expansion coefficients in this Taylor expansion will depend on the angle between them. And those coefficients we call the Legendre polynomials. You can say that this is the definition of the Legendre polynomials. Okay, once we have this expansion, L from 0 to infinity, the potential at this faraway point will be the integral of rho of r prime times sum over L from 0 to infinity r prime to the L r to the power L plus 1 PL of cosine theta. And we can change the order of integration and summation. L from 0 to infinity 1 over r to the power L plus 1. Sorry, I have this 1 over 4 pi epsilon 0 here. And what remains is this integral of the charge density. Of course, this is assuming that this is my z-axis. Now, the nice thing is this integral over here doesn't depend on my point r. It's just a constant for the given charge distribution. And we just give them a name, Q1. So this is the basic idea of the multipole expansion. So it's just an expansion at an observation point that is far from your localized charge distribution. Of course, the more interesting thing is, what do these multiple moments tell us about the charge distribution? because these will be the ones that we will be able to measure. And they basically tell us, this charge distribution, tell us how the charge is distributed in our volume. You see, whatever your charge distribution is, this is our charge distribution. Well, this looks like something like this. From a very far away point, you will just see a, let's say, a spherical charge distribution. Plus, of course, then you will see some corrections. We will be adding some segment over here, some extension over here. Some bump here. So let's say this is positive charge, this is negatively charged. Here you add some extra positive charges. Or you can say that, okay, this is the sphere plus the rest. This is the monopole plus the rest. And even the rest you can just write, you have the monopole plus you have some minus charge over here, plus charge over here, plus charge, minus charge, plus, etc. So you can basically extend your charge density as a sum over such shapes, let's say, and each one of them will only have one of the multiples, non-zero, and the other ones will be zero. So if you know that your monopole moment is non-zero, you can model it as a spherical object with a total charge. If you know that it has a dipole moment, then to that you have to add a correction where the minus charge, there are more minus charges on one side, more plus charges on the other side. If there is a quadrupole moment, the minus charges will be on one plane and the positive charges will be more on the perpendicular plane, etc.
Başlarda böyle bir charge density yapıyorduk ya işte. Dirac-Delta falan diye. Onu kullanarak böyle potansiyeli, elektrik alanı falan her şeyi yazarım.
Once you have the raw, you know the potential, you know the electric field, you know everything.
Charge'da.
Once you know raw, you know the charge anyway. So if you know the charge distribution, you don't need to worry about anything else. You don't need to worry about the method of images, multiple expansion, etc. The realistic case will be you don't know the charge distribution, and you are trying to get information about the charge distribution. For example, you would have regions bounded by conductors, and you have a known charge distribution nearby. So you know part of the charge distribution, but not all of it. You don't know the charge distribution on the conductor. Then how to find it? Or you know the charge distribution at one place, you know the potential at some other surface. Then again, how do you find the charge distribution? You know, it's easier to find the electric field than the charge distribution. But once you know the electric field, you can determine the charge distribution.
Eğer bir kare olsaydı, o method of image problemi çözerken conducting display yanında charge density var. Onun yerine bir kare olsaydı mesela.
Such a cube. You mean a cube?
Aynen.
There are no image charges. That will satisfy all your boundary conditions. Well, if you have the cube with a point charge inside, then you have infinitely many images. You have Q, there is a minus Q over here, there is a minus Q over here, there is a minus Q over here, there is a minus Q over here. These are the primary images. These images will also have their images. And the images of images also have their images. So you will have infinitely many images. So it's not that useful. But for example, if this is your problem, I would rather go with separation of variables. So what I would do, again, this is a cube. Some point charge over here. I will just divide my cube into these two regions by this plane. So this is a plane. I'm just dividing my cube into two. The point is somewhere over there. I divide my cube into two. In the lower part, my potential satisfies the Laplace's equation. In the upper part, my potential satisfies the Laplace's equation. And there is this interface between the top and the bottom. The potential has to be continuous, and its derivative perpendicular to that surface has to be discontinuous because there is a surface charge. It will be easier to solve it this way.
Shouldn't we make the cube grounded to use the images?
Well, you don't have to use the grounded image. Let's do this example. We said that, okay, for this point charge in front of a grounded sphere, there is an image somewhere over here. This is the center. Let's say this is the whole distance is d. This is d prime. The image charge is q prime. D prime is r squared over d, and q prime is minus q times r over d. This was for a grounded sphere. Now let's assume it's not grounded, but a neutral. And furthermore, since a grounded sphere, we don't really know how much charge it has. Of course, with the method of images, the charge of the sphere will be just q prime, because the conductor can attract charges from the ground or give away charges to the ground. So that's what the ground does. So if it's not grounded, the charge should be conserved. So let's say initially there is a charge q. We have this point charge over here in front of this conducting sphere. Now what? Now you see the criteria we have in this method of images is that we have to put the image charges such that these point charges satisfies our constraint on the surface. For the grounded case, the surface should be a zero potential, equipotential surface for the grounded one. Well, for the non-grounded one, for this problem, again, since it's a conductor, the surface should be an equipotential surface, plus the conductor should be neutral. Those are the two constraints we have. These two charges, plus q over here and q prime over there, makes sure that my surface is an equipotential surface. But these are not enough because my conductor is now not neutral. It has to be neutral. So that tells me that I have to add at least one more image charge to my system to make my system neutral, to make the conducting sphere neutral, zero charge, and to keep the surface of this sphere an equipotential surface, which I can achieve if I just put a minus q prime charge at the center. Now what happens, this q prime charge plus this q charge makes sure that my surface is a zero potential surface. When I add this charge over here, since it is at the center, it just shifts the value of the potential. But since it's equidistant from all the points, the surface is still an equipotential surface. Not necessarily at zero potential, it definitely is not at zero potential, but still an equipotential surface. So this configuration of charges, two image charges plus one real charge, makes sure that within this volume, the total charge is zero. as it should be, because we started with total charge Q. Sorry, I put an image charge that is capital Q minus Q prime. Within this volume, the total charge is capital Q plus the surface of my conductor is an equipotential surface. Furthermore, I can even determine the potential of my of the surface of the conductor. It is just the potential of this one plus the potential of this one. The sum of the two just gives 0. The surface of the conductor, the potential at the surface of the conductor is at the potential created by this one.
Hocam şu Q prime yazarken neden büyük Q'nun bir etkisi oldu? Merkeze Q, eksi Q prime koydum. Ama Q prime Q'dan çıkardım.
Because Q prime is the image of this one. You mean this minus sign over here? Well, one interesting thing in this problem is, let's say we have a positive charge sphere and a positive charge sphere over there. Will they be repelling each other or attracting each other? Okay, he says that they will repel each other. Okay, probably most of you are thinking that if they would repel each other, I wouldn't be asking the question, right?
If you use charges, the minus charges will be closer to the plus charges, but the same amount of charge will be divided into two parts. So, shouldn't it be charge?
Well, it depends. It depends on the distance. You see, if they are very far away, that is, if D is very large, Q prime is basically at the center. Capital Q minus Q prime is also at the center. This just behaves like a point positive charge. And that is also a positive charge, so they will repel each other at a sufficiently far away distances. Well, if this positive charge comes very close to the conductor, in that case, if the image Q prime, D prime also becomes very close to R. So if this plus Q is over here, image charge will also be over here. They are very close to each other. Furthermore, the image charge will be almost minus Q. So we have this plus Q over here, minus Q over here, very close to each other. There is, of course, the positive charge over here, but the positive charge is far away. The negative charge is just nearby. So negative charge will be attracting more strongly than the positive charge. So if this positive charge is far away, it will feel a repulsive force. If it is very close, it will feel an attractive force. And in fact, in between, somewhere in between, it shouldn't be feeling any force.
O zaman atomdaki protonlar da böyle mi bir arada kalıyor?
No. There's something else over there.
Yani hocam bu iletkenin yanına bir artı yük getirdiğimizde bu tarafta bir eksi yüklenme mi?
Yes. You see, what happens is if you bring the positive charge, this surface event, if the positive charge is at infinity, this plus Q charge, if this capital Q is also positive, the plus Q charge will be uniformly distributed over the surface. as you bring the positive charge closer and closer, what it will do is it will push away the positive charges to the other side. So if it is sufficiently close, this repulsion will be so strong that the nearby parts will be negatively charged. The other side will be positively charged. The total charge will still be positive, but the region near to my positive charge will be negative. So that which creates the attraction.
O zaman nasıl ekliyor potential oluyor şöyle? Yani bir taraftan pozitif, bir taraftan negatif içerisinde.
This is my claim. When I put the positive Q over here, this part will be positively charged, this part will be negatively charged. Right? Now, let's calculate the potential. Let's say at this point, compare the potential at that point and at this point. There will be two contributions to the potentials. One from the induced charge in the sphere, one from this positive Q charge. Now forget about this positive Q charge. The potential of the induced charges. Will this point have a smaller or which one will have a larger potential? Forget this one. I have positive charges over here, negative charges over here. This point or this point will have a larger potential. Well, you see, it's no longer a conductor. I'm not treating it as a conductor because when we are talking about the conductors, we are always saying that the charges are free to distribute. What I'm saying now is, forget about this one. I glue these charges over here. They are not free to move. They are fixed, so it's no longer a conductor. I'm not treating it as a conductor anymore. This point or this point, which one has the larger potential? Well, you see, these charges create an electric field in this direction. If you move opposite to the electric field, that is, if you move from this point to this point, the potential increases. So this point has a larger potential than this point. I repeat, the potential I'm talking about here is the potential created by only the induced charges on the sphere, not by this one. Now, this induced potential is larger here, smaller here. Now, to this one, I have to add the potential of this point charge. But the potential of this point charge is larger here, smaller over there. So that is why here I have a large potential due to the induced charges, but a small potential due to this point charge. Here I have a smaller potential due to the induced charges, but a larger potential due to this plus Q charge. Now, this small and largeness are such that eventually when you sum them up, the potential at this point of the whole system is equal to the potential at this point. You are right, this point is closer to these positive charges, but it is further from this positive charge. Whereas this point is close to these negative charges, but it is close to this positive charge. And those two effects, they just cancel each other in the sum.
Hocam şimdi hani iki tane artı yüklü küreden bahsettik ya. Bir tanesi artı diğeri eksi olsaydı o zaman çok yakın olunca birbirini itecekler.
Well, you mean this question. We have two charged spheres. Well, we couldn't find an exact solution of this one. What do you expect? If they are very close to each other, should they attract, just like this sphere and the point example? Or should they always repel each other? Well, I don't know. but I don't think they will attract. My reasoning is this one. When you say that they will attract, you are probably making the reasoning that if they are very close, this will be positive, this will be negative, this will be negative, here will be positive. So these positive and negatives, they are close by, so they will attract. Is this your reasoning?
Yeah.
This doesn't work. It doesn't work because, I mean, you see, these spheres are identical. So why should this one decide to have positive charges in this surface that is closer to the other one? They should both have the same charges at this interface. So that's why I think they will still repel each other. But I'm not sure. But you can solve a similar problem explicitly. You can solve the problem of cylinders. Take two infinite cylinders, calculate the force per unit length of the cylinder that they will exert on each other. Does it become attractive if the distance is smaller than a given limit, or they are always repelling each other? Could you solve that problem of two cylinders? Now you see, the charges are static, and you see, the attraction is due to the magnetic field. Here we are doing electrostatics. So if they carry the same charge, they will repel each other. Anyway, let's give a break. You can prepare your questions, and we can continue with your questions after the break.